Hi, everybody. Welcome back to Dave's Math Channel. I'm your host, David Tare, and this is my continuing feature on the Math Lovers book. I'm now up to section 3.3 of volume 1, which is on continued fractions. And this is my third lesson on continued fractions. Today I'm going to talk about a special type of continued fractions, namely periodic continued fractions. As you'll see, these correspond to quadratic irrational numbers. Anyway, let's begin. Like I said, we get a periodic continued fraction. That just means it's ultimately periodic. It doesn't have to start repeating right away, but eventually it'll repeat. It'll go into a repeating pattern. We can just specify which coefficients repeat by putting a line above them, kind of like you do with, repeating decimals, which correspond to, fractions. At least certain types of fractions. But anyway, so like I said, whenever you have a quadratic irrational, in other words, irrational number of the form s plus square root of d over t, where s, d, and t are all integers with d and t positive and d not a perfect square. Turns out whenever your irrational number has this form, if and only if it has this form, the continued fraction will repeat. Yeah, we can even there's an algorithm for computing it. Yesterday I gave an algorithm for computing the continued fraction of arbitrary irrational, not rational or irrational numbers. But we want to know what the period is. We want to be able to prove it as periodic and specify exactly what the period is. So the algorithm's a little bit different for doing this. It's a little bit of a complicated algorithm, actually. It's going to look a little bit funny. But this is something that you can apply a computer program to pretty easily. And I've done this myself. So I'm just going to go through the steps of this algorithm. So remember, our quadratic irrational number is of the form s plus square root of d over t. That's what we're given. We're given s, d, and t. So here's how the algorithm goes. We're initiating a couple sequences like we did for the, well, actually three sequences. A sequence of integers s sub k, sequence of integers t sub k, and also a set of integers a sub k. So how do we do this? Well, we initialize s0 equal to s and t0 equal to t. Those are the first two steps. And we initialize our index, I guess I'm calling it I here. We initialize I to 0. And then we're going to apply this algorithm recursively starting at step 4. We let a sub I be the floor of s sub I plus square root of d all over t sub I. And since s0 is s and t0 is t, you see that a0 is just going to be the floor of the number we started with, which is what it always is. A0 is the floor of the number we're trying to compute the continued fraction of. But we're going to keep computing floors later on. So anyway, and now what we do is we apply a recursive formula, s sub I plus 1 equals a0 t sub I minus s sub I. This looks a little bit funny, but it works, trust me. You can prove this algorithm works. I don't do it here. And then what we do is we want to see whether or not there was an integer j such that s sub I plus 1, that's the last of the s sequence we computed. If that was equal to any of the previous values, s sub I minus j plus 1 for some positive j, but we also want the t sub i's to repeat with the same period. So if t sub I is equal to t sub I minus j, then both s sub I and t sub I are periodic with period j, and that means we've computed the period. It's just period j. That means we put a line above the last j coefficients we computed. In other words, a sub I minus j plus 1, a sub I minus j plus 2, and so on all the way up to the last one computed, which is a sub I. That'll give us our period. And then once we do that, we're done and we can stop. I should have said stop. But anyway, if that doesn't happen, then we have to keep going. So we let t sub I plus 1 be d squared minus s sub I plus 1 quantity squared all over t sub I. It turns out this number is always an integer. I'm not proving it here, but it is. It's kind of a remarkable property of these quadratic irrationals. And then we increase our index I by 1, and we keep going. We keep repeating until we're done. Like I said, we're supposed to stop once we get to step 6. I should have indicated that here. But that's the algorithm. And now, since that's a pretty complicated algorithm, I think it's a good idea if I show you a couple examples. And I think you'll get an idea how this works when you see some examples. So here's our first example. So now we want to calculate the continued fraction of the square root of 2. And I showed you what it was yesterday. It has a very simple continued fraction with a period of 1. But let's see why we get that. So here, if we write it as 0 plus square root of 2 all over 1, so that s is equal to 0, d is 2 because that's the thing inside the square root, and t is the denominator, which is 1. Now we apply the algorithm. So when I is 0, our s sub I, that's s sub 0, that's just s at 0. And our t sub I is t0, that's 1. And so our a sub I is 1. And now we just keep applying this algorithm. So we have to calculate our next value of s sub I plus 1, or s sub 1 if you like. That's going to be a 0 t0, which is 1 minus s0. That gives us 1 minus 0, 1. That's the first number I show in red in the second column. And now we have to calculate t sub 1. So, well, actually, first we have to check the condition in step 6, whether there's an index. And so we're not done because we've only done one number. You always have to go at least 2 steps, so forget step 6. But the next step, we have to calculate t sub 1. That's step 7. So t sub 1 is going to be d, which is 2. Maybe I should flash back to this one. So we're doing step 7 now. T sub 1 is going to be 2 minus s sub 1 squared. Remember, s sub 1 was 1, I believe. Yeah, so we're doing 2 minus 1 squared, which is 2 minus 1, or 1, divided by t sub 1, I guess. Yeah, so it's going to be 1. And let's just go back to here. So yeah, I put t sub 1 as 1. We just calculated that. And now we have to go to step, we're increasing I by 1, so now I is 1. And we're going to step 4, which says a sub 1 is equal to s sub 1 plus square root of d over t sub 1. And s sub 1 and t sub 1 are both 1. So now we're getting 1 plus square root of 2 over 1, or 1 plus square root of 2. And the floor of 1 plus square root of 2 is 2. So now we keep going. Now we have to do step 5 again. S sub 2 is a sub 1, t sub 1 minus s sub 1. A1 is 1. I think everything's 1 here, if I'm not mistaken. What's t sub 1? Did we calculate? Yeah. Yeah, it's going to be 0, I guess. I don't know why it's 0. But, anyway, it turns out that condition 6 is now satisfied. We have s sub 2 is equal to s sub 1. They're both 1, and a sub 2. Yeah, I think we're gonna. Oh, t sub 1 is t sub 0. Yeah, notice that we have 2 numbers in red in the second column. S sub 1 and S sub 2, and we also have 2 numbers in a row in the T column, T sub 0, T sub 1. That means that our period is 1, and we're basically done. That means that every continued fraction coefficient from here on is going to be the same as the last one, namely 2. So our result is the continued fraction 1 semicolon 2 with a line above it. In other words, 1 semicolon 2 comma 2 comma 2. Keep going on like that forever. And I think I did say that was what the continued fraction of the square root of 2 was yesterday. We just proved it using this algorithm. Anyway, let's do another example. That was actually an easy example. And maybe I don't need to go through all the steps with this example, but this is a harder example. Um, Now we're doing 3 plus the square root of 7 all over 2. And if you apply this algorithm, I'm not going to go through every step here, but this is what you get. So we just keep calculating these sequences s sub I, t sub I, until we get repetitions, and for both s sub I and t sub I of the same period, shifted by 1. And you see that s sub 1 is equal to s sub 5. They're both equal to 1. And also t sub 0 is equal to t sub 4. They're both equal to 2. That means our period was 4. And that means that the last 4 continued fraction coefficients, starting with a sub 1, a sub 1 through a sub 4, all get repeated indefinitely. So that means our result is going to be 2 semicolon and then the sequence 1 4 1 1 repeating. So we put a line above 1 4 1 1. In other words, it's going to look like 2 semicolon 1 4 1 1 1 4 1 1 1 4 1 1 and so on. That's what the continued fraction for 3 plus square root of 7 over 2 looks like. A lot more complicated than for square root of 2, but it does repeat, and that's what it is. And you can always do this for any quadratic irrational number you start with. It might take a long time, but it always will terminate at some point. And I think I'm going to finish up by, obviously square roots are a special case of this. As a matter of fact, I already did the square root of 2 as my first example. For all these, we just set s equal to 0 and t equals to 1. And we can apply this algorithm to compute the continued fraction of the square root of every non-square integer, any non-square integer we want. And this table only goes up to 24. I guess that would be all the continued fractions that are less than 5. And you can see what they look like. And, some of them are pretty short, but some of them are kind of long. You don't really know ahead of time how long these things are. They're a little bit mysterious. But there's one other thing I think I should point out about these continued fractions. You notice that they all start repeating right after the semicolon. And that's always the case when you have a pure square root. If s is 0 and t is 1, I don't prove this here, but it turns out you get repetition right away. There's no pre-period, if you like. Sometimes you do get a pre-period. I haven't shown examples where you do, but sometimes you do. But for square roots, you don't. Another nice feature of this, you'll notice that the last coefficient in the periodic part is always twice the number right before the semicolon, which is the floor of the number we're starting with. So, for instance, if you look at the 22, that's kind of a long one. That one looks like 4 semicolon 1 2 4 2 1 8. You notice the last one's 8, which is twice 4. The same for 21. That's another long one. 4 semicolon 1 1 2 1 1 8. Looks like there's a total of 3 of these that have the maximum period for numbers less than 25, namely period 6. 13 is a little bit complicated too. That has period 5. But they do all repeat, and you can calculate their periods, and you can do this for any positive non-square integer you like. So this is nice because this allows us to, if we keep computing these continued fractions, we can get arbitrarily accurate estimates of any square root we start with. Anyway, so that concludes my video for today on periodic continued fractions. Thank you for watching. Long live math, and I'll see you guys next time. Bye.